Sir, good morning, sir. Sir, good morning.
Yeah, good morning, sir. So again, I came back to original setting.
Yes, sir. With your support only.
No, no, sir. This is our duty.
ಮಾತಾಡ್ಯಾರ ಸರ್ ಯಾವನ ಸಾರ್ದ
Late, sir. Today I didn't talk. Maybe he will be busy in meetings and all.
ಯಾ Sir, you can share your PPT, sir. Permission is given.
Oh, thank you, sir. Is it visible, sir?
Yeah, sir, visible, sir. Sir, shall we start, sir?
Yes, sir. Yes, sir.
So, good morning to all of you. So, I welcome you all for the 2-week online faculty development program on renewable energy intervention in industry, commercial, and domestic application. So, today we have with us Dr. Bogil Satyashekar, sir. Sir is from IIT Jammu. So, the sir is going to give an expert talk on harnessing the full power of renewable energy with hydrogen. So before handovering the session to Satyashekar sir, so I would like to introduce him. So Dr. Bogilla Satyashekar graduated in the year 2008 from Andhra University, the mechanical engineering branch. MTech in 2010 with a specialization in fluid and thermal science from mechanical engineering at IIT Guwahati. So after this, sir started PhD at the same institute where sir was involved in the development of hydrogen systems. So after PhD, sir joined HYSA Systems, the University of the Western Cape, as a postdoctoral research fellow in the year 2013 to continue research on hydrogen energy. So later, sir worked on a totalized hydrogen energy utilization system at a research institute for energy conservation, AIST, Japan, as a postdoctoral fellow from August 2014 to July 2016. So before joining IIT Jammu, sir worked at IIIT Design and Manufacturing, Kurnool, India, from July 2016 to September 2019. After that, sir served as a faculty in charge of mechanical engineering and student affairs. Currently, sir is working on BRICS multilateral project collaboration with Bautau Research Institute of Rare Earths, China, and Moscow State University, Russia. So DST India selected sir for the participation in BRICS Young Scientist Conclave in the energy area, which was held in Durban, South Africa from 25th to 29th June 2018. So recently, sir received Best Research Paper Awards in first National Conference on Innovations in Sustainable Energy and Technology. December 2003, 4, 2020, and 11th International Energy and Environment Symposium. July 14th, 14th to 18th, 2019. Dr. Satyashekar sir is the recipient of the Alexander von Humboldt Connect Fellowship in the year 2020 for joint research collaboration work with Magdeburg University, Germany. Sir also published 22 research papers in various reputed journals and 30 conference papers. So, sir, areas of interest are hydrogen energy, renewable energy systems, energy conservation and storage, fuel cells, absorption heating, and cooling systems. So, with this, I welcome you, sir. And first of all, I would like to thank for accepting our invitation to give an expert talk in the 2-week faculty development program on harnessing the full power of renewable energy with hydrogen. So thank you, sir, and over to you.
Thank you, sir. Thank you for your kind introduction. And also, I would like to thank you and your organization for giving me this opportunity to talk about harnessing the full power of renewable energy with hydrogen. Actually, when I am working in Kurnool, I used to travel through your institute to reach Nandyal railway station. But I never visited your institute. Okay, it's good to have talk from institute.
Please come, sir, once.
Yeah, sure, sir. So, good morning, everyone. Thank you for being here to listen my talk. So first, before going to my presentation, I'll briefly give you about IIT Jammu profile. So IIT Jammu started in 2016, okay, and the state government has allotted around 400 acres along the national highway, that is Srinagar to Kanyakumari highway. Okay, so in 2016, we started the branches with computer science and electrical engineering and mechanical engineering. So after that, later we started civil engineering in 2017. Then 2018, we introduced chemical engineering. And 2019, we started material science department. So you can see the Northeast IIT in India, IIT Jammu. So coming into this presentation, so this is my Clara presentation. First, I will introduce about the present fragile energy economy. Then I will discuss about energy and CO2 emission trends. Then we'll see why we have to choose the hydrogen as a clean secondary energy carrier. Then we'll also see different elements of hydrogen economy. Then we'll go to talk about the suggested future energy economy. So I would like to quote here from Jules Verne. So what he says in 19th century, that is 1874, he told that hydrogen from water electrolysis is to replace coal. Okay, so water will be the coal of the future. So that he predicted in 19th century. So now we will discuss about the global environmental challenges. We have like past several years, we have economic growth. So that is also bringing some environmental issues. Okay, that is like you have a climate change, the air quality, and energy security. Okay, so basically these things challenges. It's giving opportunity for automotive industry to change. Okay, so if you see this climate change, we want to reduce the CO2 emissions. Okay, so then we have agreement in Paris 2050. We want to, India will reduce the CO2 emissions before that. Then we have air quality problem like regulation of NOx and all. So some countries has already taken some policies to reduce the NOx. And again, we have another problem regarding that energy security. So now recently the Prime Minister has taken that one more policy, that step, that is Atmanirbhar Bharat, and means self-dependency. Okay, so in that case, we have to look towards the renewable energy development. Then, so based on all the things, the automotive industry is facing challenges as well as it is opportunities. So based on this context, so we have to avoid these fragile fuels. So again, we divided this fragile fuel phase out into two processes. The first phase, it is phase out of fragile fuel vehicles. Then we are going to phase out of fragile fuel based power plants. Then maybe many of you knows about this today's energy system, that is global hydrocarbon economy. So if you see today's the energy production, most of them like 75% is coming from oil, gas, and coal. Okay, so that we are using coal or oil or natural gas to get the energy. Like we are using for processing industries as well as transport, okay, and for power generation. So by combusting these fossil fuels, we are releasing like CO2 and other greenhouse gases to the environment. So because of this, we are increasing these emissions and global warming effect. So you can here you can see how this our global energy, primary energy demand we are achieving. So we started before 19th century using the biomass. Okay, then initially the 20th century we expanded that our energy from coal as well as oil for transport. Then, so because of the steep rise in the Western living standards, so the energy demand increased drastically. So after 2000, everyone knows that there is a rapid integration in China, means rapid development in China. Then the primary energy demand increased a lot because the China population is huge. Okay, the proportion is huge with respect to the world population. Then after that, like India also improving this standard of living. So because of this, all the things, the energy demand is increasing. So you can see even 20 after 2030, so the energy demand is almost constant, but still it is increasing. But there is a prediction that after 2030, so this fossil fuels usage is coming down, and we are increasing that the renewable energy share in the primary energy demand. So here I want to show the energy balance, the trade-offs for different countries. So you see that the red one is a deficit country and the blue is surplus country. Okay. So if you see USA in 1990, it is a deficient country based on the oil, gas, and coal. But now 2017 2040, it is surplus country. Okay. Again, if you see the Western countries like European Union, so those are, even though after 2040, those are deficient countries based on the fossil fuels like oil, gas, and coal. But if you see the Middle East as well as Russian countries, those are surplus countries. Again, if you see Southeast Asia, those are deficit countries, even though it is going to 2040. So what is this impact? So if you see the India imports in 2019, so we have around $480 billion we imported from other countries. In that, if you see 33%, it is going to import the mineral fuels, oils, and distillation products. So if you want to improve your economy, or if you want to go for that Atmanirbhar Bharat self-sustainability, then we have to reduce these imports from other countries. Then only we can improve our economy. So here I would like to show that the share of renewables from 95 to and at present 2020 and the prediction for 2050. You can see very less share of renewable energy during 1995. Now it is good amount of share 2020, almost 27% we have the energy generation from renewable energy. So if you see the 2035, it is going to 51%, and 2050, it is going for 73% coming from renewable energy. Uh, if you see in India, maybe in 2020, the energy demand, maybe after 2040, the energy demand is going to be double because our living standard of living is increasing drastically because of this energy consumption from homes as well as industries, some other industrial process. So because of that, we have to generate so much of energy, basically that electrical energy. So if you want to generate that much energy, you can't depend upon the fossil fuels. So you have to go with respect to the renewable energy share. So then only you can reduce your CO2 emissions with respect to this Paris Agreement. So here I want to show that the world total consumption by region. If you see, the China is increased from 2000 drastically. Then maybe after that, the India is increasing. If you compare with other OECD countries, that is from after 2000, their share is almost same. But so if we see China and non-OECD countries like India and all, so this the consumption is increasing drastically. So here I want to show the oil, the total final consumption by sector from 1971 to 2018. You can see the oil consumption is increasing majority from road compared to other process. Okay, so the road, the usage of oil is increasing day by day. So here I want to show the CO2 emissions reduction. This is only prediction. You can see the transport, and you can see the second one is long distance transport. Okay, so there is a two difference here. The first one is transport, the second one is long distance transport. So if you see how you are going to reduce the CO2 emissions from different ways. So if you see in transport, we are going with introducing hydrogen, and we are going with bioenergy, and we are going with other renewable energies, and we are going with some electrification of automobiles. So if you see the difference from transport to long distance transport, you can see the difference in hydrogen. Okay, so the hydrogen component is more in long distance transport compared to the transport. I will explain later why this hydrogen is more useful for long distance transport compared to within the city. So it is clearly shows that if you want to reduce the CO2 emissions, then you have to go with hydrogen for transport vehicles. Then, if you want to discuss about the energy economy, this for concept of sustainability. So without having any global warming effect, as well as without depend upon other countries. So basically, the energy source should be reliable, so delivered at any time, and it should be safe and no unacceptable danger to population. Then economic wise, it should be acceptable prices like your solar PV. Solar PV is now the tender cost is you will get 2 to 2.5 rupees per kilowatt hour, and no unacceptable impact on environment, and long-term availability of energy carriers. These are our requirements coming from the concept of sustainability. Then we have how to tackle this global warming. So we have to tackle global warming from both sides, from demand side as well as supply side. Okay. So from demand side means you have to design very efficient appliances like your air conditioning systems and your transport vehicles. Okay. Then you can reduce the CO2 emissions. So there is a prediction that if you go for this high efficient end user applications, then you can nearly reduce 80% of project CO2 by 2030, coming from only demand side. Okay, so out of 100% the CO2 reduction by 2030, so 80% is coming from only demand side. Then obviously supply side, we have to move towards renewable energy to reduce the emissions. Okay, so these are the projected CO2 reductions from various sources by 2030. So you can see the majority share is coming from 35% from mileage. Okay. So by using this hydrogen or battery vehicles, you can reduce the CO2 emissions contribution compared to other share. Then I will show some the policies taken by different countries. Okay. First, if you see European Union, they agreed to cut around 30% the trucks and bus CO2 emissions by 2030. Okay. Then, if you see the policies from Norway, so they want to ban this combustion engine vehicles from 2025. Okay. So after 2025 in Norway, they won't sell any combustion-based vehicles. If we take again like UK, France, they want to ban these diesel engine vehicles from 2040, and so Germany also has taken some policies to reduce these internal combustion vehicles. As well as we can see this Asian countries, China also adapted that it is going to with hybrid vehicles, and you can see Korea is planned to ban the diesel vehicles from 2030. So I can show something like the OEM's green car strategies. These are the big companies in automobile sector. Okay, so the Volkswagen is to stop the making gasoline diesel cars in 2020s. What you can see, what is the head is says in the 2026 will be the last product start on combustion engine platform. Similarly, Hyundai also introducing some eco-friendly vehicles. Okay, and the Toyota also eliminate the gasoline cars by 2040. The Volvo also use electrical motors in all cars from 2019. So these are the various car strategies, okay, to go for green vehicles, okay, and to reduce this internal combustion vehicles. So we have two options for going for the green vehicles. Either you can use the electricity based vehicles like battery vehicles, or you can go for hydrogen based vehicles. So you can see the replacement of oil for transport sector, because most of the countries, the policies are taking that by 2030 or 2040 they want to ban the fossil fuel vehicles. Then what are the long term options we have? Natural gas, it will reduce the emissions compared to the diesel and petrol, but still it is not a long term solution. Then we have second generation biofuels. Okay, so these can also reduce the CO2 emissions, but the problem is that it can impact the food situation, like we are using land, okay, and impact an environment like cutting of forests, okay, to cultivate these biofuels, and use of fertilizers and irrigation problems, water problem. Then third option we have the electrical drives. You can use batteries. Okay. Then the fourth option is the hydrogen as a fuel. So here we have to remember that the hydrogen has to produce from renewable energy. Okay. Then only we can say this is green fuel. So if you see the green car strategy, the fuel economy improvement, okay, that is the first choice. You are going with new engines and weight reduction, okay, improving the efficiency. Okay, the next stage, now we are in next stage, that is hybridization. We are going to have both your combustion engine as well as you have some battery, that is electrification. So you have both combined. First you use battery, then if its battery is dead, then you can go with this ICE engine. So that is hybridization. And the next level, we are going to have the electrification, this pure clean mobility vehicles. Either we are going with battery vehicles or we are going with hydrogen fuel vehicles. Okay, so here I'm going to explain what is the difference between the fuel cell and battery. Basically, these two are electrochemical devices. Both are same principle, it will work, but these are not same. If you see the fuel cell, so the chemicals continuously flow to the fuel cell to generate the electricity. Whereas if you see the battery, the chemicals stored inside will be used to convert for electricity. Then if you see the fuel cell, it will produce electricity continuously as long as you supply the fuels. Whereas battery, once you used, it will goes dead after certain period. Okay, if it is rechargeable battery, you can recharge again. Okay, if it is not, then you have to throw away. So that is the main difference between the battery and fuel cell. So here I want to show this the principle of fuel cell. So this fuel cell will have two electrodes, one electrolyte similar to our battery. Okay, so you supply the hydrogen from your source to the electrode from anode side. So what would happen here? So it will dissociate into the proton and electron. So from this membrane, the proton will transport, whereas it will stop the electrons. Okay. So the electron will go to the external circuit. Okay. Then it will come with the cathode side, and it will react with proton, electron, and oxygen from the air, and it will produce water vapor or water. So this is the principle of the fuel cell stack. So basically, it will convert the chemical energy from the fuel directly into electricity. So it can produce this electricity with high efficiency compared to your IC engine. So efficiency of fuel cell is higher than IC engine efficiency, and there is no noise. Okay, because there is no moving parts. We have a small blower to supply this air to the fuel cell stack, and the advantage is it can generate the power in stable way and reduce expensive power transmission and less pollution. Reaction, we call this is exothermic reaction. Basically, it will generate some heat. So that heat also we can use for some other applications that I will explain later. So here I want to show some small video about this fuel cell. Then you can understand. So it was nice video from Ballard. It is actually Ballard is the one of the pioneer in manufacturing the fuel cells. Then I'll show the difference between the fuel cell and battery. So as you see now, you can see the battery-based vehicles on the road, but the fuel cell-based vehicles are still in development mode, and some are running in like in Japan and USA and some European countries. But there is a small difference between these fuel cell vehicles and battery vehicles. So you can see this the energy storage system volume. Okay, so if you use this battery-based vehicles, you can see if you increase the range, the volume is increasing drastically. Means maybe your battery, the volume will be very high. So obviously your automobile size also will vary, increase. Okay, then your the electricity consumption will increase. So obviously, for battery vehicles, there is no competition for low range. Like if you go for within the city, so the fuel cell vehicles cannot compete with battery-based vehicles. But if you go for like long range, like more than 150 kilometer miles or more than that, like for buses and the heavy trucks, so you cannot use battery because this battery, the recharge time is high. Okay, so it can run only for like 50 to 100 kilometers. Okay, so again recharging it will take time. So if you go for these hydrogen based vehicles for long range applications, just for you can refill within the 5 minutes, and you can go for like long range like 500 or 1000 kilometers. So you can see if you see this energy storage system value for fuel cell vehicles, okay, the volume is increasing slowly. Okay, not like batteries drastically. Okay, so economy wise, for long range applications, the fuel cell based cars are better than the battery based cars. Obviously, in short term, we have more sales from battery based vehicles, but maybe after 1 decade, we can see the real market for fuel cell based vehicles. So what is the difference between this hydrogen and electricity? So basically, these both are energy carriers. Okay, so they can meet the requirements of all user sectors. If you see the difference, you can store the hydrogen easily compared to electricity. So, but if you see the electricity storage cost is higher compared to hydrogen or thermal energy storage cost. So that's why we cannot store this high amount of electricity in batteries. Okay. So as I said, the electricity cannot be stored in large quantities. Okay. So if you want to have large quantity storage, then you should have a lot of batteries. Okay. Again, the cost, the capital cost will be higher. Again, one more problem with the batteries is the durability. So how many times the refilling, how many times it may come, we don't know. So why hydrogen deserves attention? So basically, you know, like hydrogen is the smallest of all atoms, and it is having high energy content per byte. If you see compare with the gasoline, it is having 3 times more energy per unit weight. Because that is the major advantage of hydrogen. Why we should consider hydrogen as a energy carrier. Then one more drawback of this hydrogen is it is having very low energy density per unit volume. It means that it requires large storage tanks. But this drawback we can reduce by compressing the hydrogen. Or we have other storage methods to increase the storage capacity. So you can see we started 19th century before that. We started with solids, then we moved slowly to liquids. Then the future will be with gases. Okay, maybe after 2050. So the hydrogen play a major role in transport sector. So here you can see what is the hydrogen energy system, means from production to end user. So obviously you have to generate the hydrogen from various sources, because hydrogen will not, is abundant in nature, but it is not available in free form. So it is combined with, like, in the form of water H2O, or it combined with some fossil fuels like natural gas, CH4 and all. So you want to generate hydrogen, you have to supply the energy. Okay, that is important factor for this hydrogen economy. Once you generate hydrogen, that can be used for transport applications, residential applications, like commercial applications. Okay, so this will continue. The cycle will continue. So here I will show this, the world hydrogen economy. So before that, we have seen that hydrocarbon economy. Now we'll see the world hydrogen economy, that is future economy. So here we are producing hydrogen by using the renewable energy sources. So you cannot produce the hydrogen from the fossil fuels. Again, it will give this pollution. Okay, so you have to generate the hydrogen from renewable energy sources. Then only it will call as the clean energy carrier. Okay, so that hydrogen we can use for transport or some other purpose like combustion. Okay, to generate thermal energy. So in this cycle, you can see it is we are using water for generating hydrogen. Again, when your combustion or producing electricity in fuel cell, again it is forming water. So by using this hydrogen as an energy carrier, we are not producing any harmful gases to the environment. So as I shown in the video, if you see this hydrogen fuel cell electrical vehicle, we have different parts. Like we need hydrogen storage system, because to supply the hydrogen to produce electricity for a long time. Then obviously we should have fuel cell to convert this stored hydrogen into electricity to drive your automobile vehicle. Okay. Then we should have motor. Whatever you produce electricity, that will be used to produce the mechanical energy by using motor. Then we have a small battery system to absorb these fluctuations, the energy production from fuel cell as well as the demand side. That it will be very small quantity compared to this fuel cell size. Basically, this is the fuel cell based car. So these are the parts involved. So if you see this, the electrochemical reaction of hydrogen and oxygen. So as you know that if you have combined with hydrogen and oxygen, okay, in fuel cell mode, obviously it will generate electricity plus some water. Where whenever you want to produce the hydrogen, so in opposite side, use water and electricity to produce oxygen as well as hydrogen. So this is the basic reaction for fuel cells as well as electrolyzers. So here you can see the different types of fuel cells. So we have PEM fuel cell, that is called the proton exchange membrane fuel cell, and we have direct neutron fuel cell, we have alkaline fuel cell and phosphoric acid fuel cell, and we have molten carbonate fuel cell, and the final solid oxide fuel cells. Okay, so we have a number of fuel cells. Then these fuel cells, the operation is little bit different with compared to other fuel cells. So you can see some fuel cells we are supplying hydrogen, and some fuel cells we are supplying some like fossil fuels and all. Then if we see this the temperature range, for each one we have a different temperature range. So the applications also will be different based on this temperature range. Just we'll see here. So if we see this direct methanol fuel cell, here we are using electrolyte as proton conducting membrane, similar to the PEM fuel cell. But if we see this alkaline fuel cell or phosphoric acid fuel cell, we have different electrolytes, like one is concentrated phosphoric acid, okay. The second one is potassium solution. Then if you see the molten carbon fuel cell, it is using the molten carbonate as electrolyte. And if you see the solid oxide fuel cell, we are using the ceramic material as an electrolyte. So first three, these are low temperature fuel cells. We'll call this direct methanol fuel cell and proton oxide fuel cell and alkaline fuel cell. These are the low temperature applications, whereas the next three are for high temperature applications like PFC, MCFC, and FCFC, the solid oxide fuel cell. Solid oxide fuel cell actually it work very high temperature range, 800 to 1000 degrees centigrade. And also the fuel supply is different for different fuel cells. Some fuel cells use hydrogen as a fuel, and some we are supplying like methanol or natural gas, like we are using that reforming to produce hydrogen. The power ranges also it will be different. Some are we can use for low range of applications like watts to kilowatts, and some are we can use for like megawatts, like solid oxide fuel cell. So based on this temperature range and based on the power range, we have different applications. Okay. For if you see this automobile vehicles or small applications, you can use direct methanol fuel cell or proton oxide fuel cell. Okay. So basically, the proton oxide fuel cell is the best fuel cell for automobile vehicles because it is the BOP, the balance of plant is simple, and the starting time is very less compared to other fuel cells. Okay, and also easy operation. For space, we are using that alkaline fuel cell from long back, and if you see that high temperature fuel cells are high power range fuel cells like molten carbon fuel cell and solid oxide fuel cell. Here, these applications we can use for power plants. Basically, this can produce the CHP applications, like you can generate both heat and power from this fuel cell. We can generate the power from this waste heat. That is the advantage of solid oxide fuel cell. So basically, this solid oxide fuel cell can be worked as a small power plant. That is the CHP power plant. So if you see, as I explained, this polymer electrolyte membrane fuel cell, the PEM fuel cell, is best suitable for transport applications. So here we can see the brief history of the PEM fuel cell. Basically, the concept it is started in 1839. Okay, that is given by Sir William Groove. It is demonstrated the basic operating principle of fuel cell. Then it was reinvented by Francis Bacon. Okay, started working on practical fuel cells in 1937. Okay, by the end of 1950s, he was able to develop 6 kilowatt fuel cell. It is the tremendous effort from Bacon, because in 1937 itself, he has developed a 6 kilowatt cell. Then the first practical applications is done by General Electric, that is called GE, for the Gemini program in 1960s for NASA application. Okay. Then we started for terrestrial applications. Okay, so General Motors experienced with fuel cell powered van with cells from Union Carbide in mid 1960s. After that, actually they forgotten for terrestrial applications this fuel cell, only used for space applications. Again, the fuel cells re-entered in 1989. So Perry Energy Systems and Ballard demonstrated a PFC powered submarine, and 1993 Ballard, as shown the video, demonstrated PFC powered buses. Okay. After that, the movement started to develop these PEM based fuel cells for transport applications. So this is the brief history of PEM-based fuel cell. So here you can see the PEM-based fundamentals that what you have discussed and what I have shown in the video. So here we have a bipolar plate. Basically, it will supply the fuel as well as it will remove these reactants. And here you can see we have a gas diffusion layer. Okay, basically it will distribute the fuel as well as reactants. Then once the fuel is the hydrogen is coming to this catalyst layer, it will dissolve into like proton and electron. The proton will transfer, means transport through your membrane. Okay, then again here one more reaction with proton, electron and oxygen coming from gas diffusion layer. Okay, it will form as a water and it will remove from this side. This is the basic structure of PEM-based fuel cell. Okay, here you can see the basic reactions at anode. As I explained, the H2 will be dissociated into protons and electrons, and cathode side again it will all the oxygen and proton electron will combine form as a water vapor. The overall reaction you can see the hydrogen plus oxygen it will go to hydrogen, means water. In electrolyzer, that is opposite. We are supplying hydrogen, means water, as well as electricity, will generating hydrogen. So if you see the heat of reactions, if you compare with HSV, the higher heating value, that will be around 286 joules per mole. Whereas if you taken as LHV, that will come as 241 joules per mole for this reaction. If you see the delta G, that will be around 237 joules per mole. So if you want to calculate this electrical work from the fuel cell, so here you can use this equation to calculate how much electrical work is generated from this fuel cell. So here the N is number of electron per mole of fuel, and F is the Faraday number of charge per mole of electron, and the E is the potential, how much potential from the fuel cell. If you see that, assuming that all the Gibbs free energy that could be converted into electrical work, so the maximum cell potential we can achieve theoretically, that will be around 1.23 volts. That is the maximum voltage from one cell. Okay. So based on this, you can calculate how much efficiency you can generate from fuel cell. So if you go with HSV, that you can produce around 83%, convert from hydrogen to electricity. Whereas if you calculate based on LHV, that will give 94%. Okay, so this percentage is very high in terms of the energy transfer from one form to another form, like a chemical to electricity. So if you see this IC engines, we have the efficiency is just 30 to 50% maximum we can get. Compared to that fuel cell is highly efficient compared to IC engines. Maybe you may have some doubt how it can convert more efficiently than Carnot, because Carnot says that is Carnot engine is the highest efficiency. So there is a myth here. Basically, this PEM fuel cell is not a heat engine but an electrochemical engine. So therefore, this Carnot efficiency limit is not applicable here. Okay, so that's why we can achieve higher efficiency. But if you see the practical efficiency, we can achieve maximum 60 to 65% from the fuel cell. That is the practical range of efficiency of fuel cell compared to the theoretical limit. Now we'll see the different components of fuel cell. Okay, so first we'll see the electrolyte. Basically, this is a polymer membrane electrolyte. Okay, so this PFC derives its name from polymer electrolyte membranes. The role is these membranes are solid electrolytes that can conduct proton but impermeable to gaseous phase. Means this electrolyte has to transport only protons. That is the main role. if you see the materials, what we are using here, we are using this perfluorocarbon sulfonic acid ionomer. Basically, these are called as Nafion membranes. This is the Nafion is the best known membrane till now that is produced by DuPont company. So thickness, if you see, that is very small, 20 microns. The desired properties for electrolyte is, as I said, it should conduct the protons, okay, efficiently, and also we have that it should chemically inert and it should be mechanically strong against swelling. So this is the basic function of electrolyte. Then if you see the catalyst layer in PEM fuel cell, the catalyst layer very thin. Okay, it is in between the electrolyte and gas diffusion layer that I have shown the video as well as previous slide. The role, it is the desired reactions takes place at this site and current is produced. So the materials, basically we are using the platinum is the best material for this catalyst layers. But the problem is that platinum is very costly and available only in some countries. Okay. Then if you go for again platinum based fuel cell or batteries, again battery materials also available in some materials, some countries. Again, you have to depend upon the import. So majority of efforts are ongoing to develop the low cost alloys that could replace the platinum. Okay. So here the thickness of this catalyst layer is less than 10 microns, could be thinner in anode side compared to cathode side. The desired properties, we need higher activity, obviously, to convert from one form to another form, resistant to corrosion and coagulation. Then we'll see the gas diffusion layer. What is the function of gas diffusion layer? It is in between the catalyst layer and bipolar plate. Okay. The role, as the name suggests, okay, it is the porous layer for distributing the reactants even to reaction sites and remove the product. And also another task is it should connect the electrically the catalyst layer with bipolar plate to transfer this electrical energy, and it should have high thermal conductivity to remove the waste heat from the cell. So materials we have like carbon paper of carbon cloth and other materials. Thickness here is this gas diffusion layer little bit thicker than your catalyst layer, that is around 100 to 200 microns. If you see the desired properties, basically it should have high porosity to ensure the gas phase diffusion, okay, and it should have hydrophobic to help remove the liquid water, because if this liquid water is staying there, it will stop these reactants to flow to the cell. Okay, basically it will clog without supplying the hydrogen as well as oxygen. Then your fuel cell, the function will stop. And also it should have high electrical conductivity and corrosion resistance. Then final, we have a bipolar plate. Basically, this is called as current collector. Okay, this is the outmost component of the gas channels. Okay, supply either for reactions or removing the products. Basically, this is the outer layer of the any cell. The role here, it is connected to the outer circuit and drive the current, and also remove the waste heat generated in the fuel cell, because as I explained, this reaction is exothermal reaction, and it should provide structural strength to the total cell. Okay, so the material is basically we are using graphite. Okay, so thickness, this is the highest thickness material in the fuel cell, that is up to 1 mm. The desired properties, obviously it should have high electrical and thermal conductivity, because to transfer this electricity as well as heat to adjacent layers, and corrosion resistance and mechanical strength. So coming to the water balance, why we have to balance the water in fuel cell? Because this PEM fuel cell, if you want to have highest amount of this proton exchange, then obviously it should have always should be in hydrated mode. Okay. Again, Another problem is that water clogging problem, okay, in cathode layer side. So you should not have too much water again, because it will block the both your reactants, okay, as well as your gases. Okay, so you have to maintain the proper water balance in the fuel cell to function continuously. Okay, so I'm stopping here this basics of fuel cells. Maybe our collaborator, the Professor Nagasri will explain the design of fuel cells, I think, in Monday class. Now I'm going to the hydrogen production, the present technologies. Basically, at present, we are producing hydrogen from various processes. That if you see, the major stakeholder is from the steam reforming of natural gas, that is producing around 48%. Okay, then we have the partial oxidation of heavy hydrocarbons, that is coming 30% of global production, and the partial oxidation of coal, that is producing around 18% of hydrogen. Then we have electrolysis, that is around 4% of global production. But if you want to use hydrogen as a green fuel, okay, or clean energy carrier, you have to produce the hydrogen from renewable energy sources, not from like either from steam reforming or partial oxidation, because at present this hydrogen production cost from electrolysis cost is higher than the other three processes. That's why majority is we are producing from this steam reforming or partial oxidation of heavy hydrocarbons. But now if we see this electricity cost coming from solar PV, that is decreasing drastically. Now you can get around 2 to 2.5 rupees per kilowatt hour. So this hydrogen production cost also will reduce further. Then once you produce hydrogen, then next element is your storage. So what are the different options available for hydrogen storage? We have like high pressure gas cylinders, then we have a liquid based hydrogen tanks, then we have metal hydrates and liquid chemicals, and we have some porous materials to absorb this hydrogen. And again, we can also store hydrogen in carbon nanomaterials and glass microspheres. So we'll see one by one. First, we'll see the conventional methods. The conventional method is first the high pressure gas cylinders. So here, as I told, this hydrogen is very light gas. So it will take huge volume if you store at atmospheric pressure. So that's why to reduce the volume, we are pressurizing the hydrogen up to 800 bar. Okay, so the volumetric density increases with storage pressure. If you increase the pressure, obviously the volumetric density increases. Obviously, you have very good, this hydrogen having very good granular density, but the pure, the low volumetric density you can enhance by increasing the storage pressure. Okay, but the problem here, it is not safe to have like 800 bar or 700 bar cylinder with you in the vehicle. And one more, the disadvantage is that if you want to pressurize this hydrogen for like 300 bar, so you have to spend around 18% of the hydrogen energy. Okay, to compress the hydrogen to 200 bar to 300 bar. So it means that already for compressing itself, you are losing the 18% of energy from the hydrogen. Okay, so that is one of the main drawback of this high pressure gas cylinders. Then if you go for this liquid hydrogen, okay, the second option we have liquid hydrogen. As you know that this hydrogen can be liquefied at 20 Kelvin at ambient pressure. Okay, you have to go very low temperature to liquefy the hydrogen. Okay, so the density at 20 Kelvin is huge, that is 70 kg per metric cube. Okay, so it's very good density to have for transport applications. But again, here also we have some drawbacks. One is the boil-off losses. Okay, because you have atmospheric temperature around 300 Kelvin, and your tank temperature inside is less than 20 Kelvin. Obviously, you cannot arrest that heat transfer. Okay, the total heat transfer you cannot arrest. Whatever you can use the insulating materials. Because of that, obviously some boil-off losses will be there. Okay, and also you cannot close this cylinder. Okay, because if you close the cylinder, this pressure will increase. Okay, you have to remove the vapors produced in the tank. So in this way, you lose some energy content. And again, one more main drawback of this liquid hydrogen is, so for liquefied hydrogen, you have to spend around 35% of energy content in the hydrogen. If you calculate how much amount of the mechanical energy you have to give to produce the 20 Kelvin, that is around 35% of energy stored in the hydrogen. So it means that you can have only 65% of energy. Now we have a third option, that is metal hydrates. So by using the metal hydrates, you can store the hydrogen at ambient temperature and ambient pressure. So you can see I am comparing here various storage methods for hydrogen. You can see this grams of hydrogen stored per unit volume. Okay. If you compare per unit volume, okay, the metal hydrates are storing more amount of hydrogen per unit volume space compared to even liquid as well as compressor hydrogen. Here in this picture, you can see how much volume it will take. Okay, for this vehicle, you can see if you use for a 200 bar cylinder, you need this much tank to accommodate in the vehicle. If you go for liquid also, you need somewhat big tank to store the hydrogen. Whereas if you go for metal hydrates, the storage volume is small compared to other two options. So you can store easily with using metal hydrates. Okay, for transport applications. Basically, this Department of Energy of USA, the target is for transport vehicles, we need the storage capacity around 5-8%, and operating temperature should be it should be minus 20 to 50 degrees centigrade. Okay, and the refilling time, like you should take only 1 minute for refilling the around 0.5 kg of hydrogen. And the delivery pressure from the solid cylinder should be above 2 bar, because this has to supply to the fuel cell to generate the electricity. So these are the storage container requirement from Department of Energy USA, that is called as DOE. So these are they have set some conditions to design the proper storage tank for hydrogen based vehicles. So till now, there is no material or no storage media to shoot this all the parameters. Maybe some are can satisfy maybe 2-3 requirements, but some are fail with another requirement. Still, research is going on to satisfy this all the conditions set by the DOE. If you go for this solid state hydrogen storage, again we have different materials to observe to store the hydrogen at various operating conditions. So you can see the physically bound hydrogen. You can use the carbon nanotubes and other carbon structures, and like you can also use geolites, and you can also use like metal frameworks, MOFs. Okay, so this storage capacity is different. Like 5% you can go for carbon nanotubes, and 2% for geolites, and 4.5% for metal frameworks, MOFs. Again, if you see the carbon nanotubes, even though it's going with 5%, the problem is that the low temperature. You have to operate this storage tank to 77 kelvins. Okay, and the pressure is again 40 to 100 bar. Okay, again these are deviating from our DV target. Okay, so need of the cryogenic temperature for high weight percentage is the drawback for this carbon based materials. Again, if you see the GLX, again same problem. You have to go for the cryogenic temperature around 77 Kelvin and 15 bar pressure requirement. Again, it's a low weight percentage and need of low temperature. The MOFs also, again, you have to go for cryogenic temperature to have high storage capacity up to 4.5%. Then, if you go for chemically bond hydrogen, okay, chemical option, we have a metal hydrides and we have a complex hydros. Then, if you see this magnesium-based hydrogen Li, that it can store 5.4% at 300 degrees centigrade and 1 bar. A little bit temperature is high. Okay, so it means that we have to give high temperature to produce to dissolve the hydrogen from the magnesium-based alloys. That is the one of the drawback of magnesium-based alloys. And we can use this low temperature applications, metal hydrides like MM-based, bismetal-based alloys or titanium-based alloys. You can store easily 1.6 to 1.8%. And the advantage is here the operating conditions are near to the atmosphere, like 30 degrees and 20 bar. Only the drawback is low weight percentage compared to our target, but still we can use for transport applications safely. And also energy point of view, those are the best materials to store the hydrogen for transport applications. Then you can go for complex hydrides. These are like, it is having very high amount of storage capacity, like 18.4% or 10.6%. Again, these are having very pure kinetics. Okay, and also one more drawback is the cyclic stability. Okay, these are the main issues with respect to complex hydrides. So still these are in research mode. Then if you see the metal hydrides, the reversible chemical heat storage. Okay, so here we are using some intermetal compounds forming a line of different metals by either using ball milling or melting for hydrogen storage operation. So if you see this, the reactions, absorption is like you have a material, metal hydride. If you combine with hydrogen, it will form as a metal hydride, and also because the reaction is exothermic, it will release some heat. Then, if you want to get back this hydrogen, what you have to do is you supply heat simply. Then obviously this metal hydride will become again, it will release hydrogen and it will become intermetal. So the operation is very simple. If you want to generate the stored hydrogen from metal hydride, just you supply the heat at different operating conditions. You can dissolve, you can get the hydrogen from the storage tank. So if you see this, the heat values, like we have 15 to 75 kilojoules per more. If you go for this low temperature applications, that will be around, you can have 50 to 30 kilojoules per more. Whereas if you go for magnesium based hydrides, then you have to give high amount of energy. Okay. So what are the applications of metal hydrides? You can see we can use for like hydrogen storage, hydrogen compressor, and various other energy conversions like refrigerator, heat pump, and thermal storage, and heat transformer. Basically, these reactions, like we can call the heat-driven mass transfer phenomenon, because we can control this hydrogen absorption as well as desorption by controlling the heat transfer in the storage tank. If you see this basic absorption process, again, it is having some 5 subtasks. One is the physics option. Basically, the hydrogen molecule will initially stick to the metal hydride surface. Then the chemical option will happen, means the molecule will divide into 2 atoms. Then it will penetrate into your surface, metal hydride surface. Okay. Then it will take diffusion, and we have a nucleation, and growth. So this will become metal hydride. The absorption process completes. Desorption, obviously, it is reverse from hydride decomposition. Again, we have diffusion, the surface penetration, and it is recombination and desorption to gaseous phase. So here you will get the hydrogen in desorption process, whereas in absorption process, the hydrogen will be absorbed by metal hydride. So you can say this metal plus hydrogen become metal hydride. In absorption process, it will release heat, external negation. In desorption process, just you supply the heat. Okay, again it will recombine into metal plus hydrogen. So why you have to use this metal hydride as a hydrogen storage? So it can store hydrogen at room temperature and atmospheric pressure. High storage capacities up to we have 7-8%, and ability to absorb release large amount of hydrogen gas many times without getting deterioration. Means you can use for like different cycles like 1,000 or 2,000 cycles or 3,000 cycles without having any deterioration in the reduction in the storage capacity. That is the main advantage of metal hydrides. And basically these metal hydrides environment friendly and also utilize low grade thermal inputs for different energy conversion devices. I will explain later what is this energy conversion devices. And safety storage media, particularly for mobile applications, because you are storing hydrogen at room temperature and atmospheric pressure. So can be effectively used for more than 15,000 cycles. Okay, means absorption and desorption. Okay, here you can see the PCT isotherm for hydrogen absorption. So once the hydrogen absorbs, the composition, the concentration increases. Okay, after the limit, again the pressure will increase. Okay, so these are at different temperatures and different pressures. So based on this, the pressures and temperatures, we can construct many engineering applications by using these metal hydrides to like convert from the energy from one operating conditions to another operating conditions. So we can energy conversion takes place from like high temperature to low temperature and low temperature to high temperature. So these are the various energy conversion devices. Like you can use these metal hydrides for heat pump and refrigerator and heat transformer, thermal storage. So maybe I think if the Professor Anil Kumar will explain about this various applications of these metal hydrides. So the advantage is like it is basically environment friendly. It can use low grade heat energy and compact in construction. And if you see these devices, there is no moving parts. Okay, so no liquid circuit. Okay, hence it can operate at any orientation, not like our absorption systems like heat pumps. And these reactions can be controlled by varying supply pressure and temperature. As I explained, these are heat driven mass transfer phenomena. So I have explained why hydrogen is the alternative fuel, that the limited availability of fossil fuel and the increasing energy demand. And we can also see that hydrogen having highest the gravimetric energy density compared to gasoline. It is almost 3 times higher than the gasoline engines. Okay, and also this the hydrogen based fuel cell vehicles like devices, this can convert this energy from one form to another form by up to like 90% you will get, whereas in case of IC engines you will get only 40% the conversion efficiency. So if you use this hydrogen from renewable energy sources, then it can potentially an adjustable substrate of energy. Okay, you can use as a energy carrier for transport applications like your electricity based vehicles. So here you can see various properties of the hydrogen. Okay, so you can see the hydrogen having the highest amount of calorific value per kg of hydrogen compared to like you see diesel and you see gasoline and petrol. Now I'm going to explain this. The practical research work is done on the transport vehicle. So that I have done at HISA systems. So here you can see this metal hydride system for hydrogen storage and supply to low temperature PEM fuel cell for automotive application. So this hydrogen cylinder we adapted for golf cart that I will show in the next slide. So you can see various parts of this storage cylinder. We have stainless steel container. This container is basically SS316. Okay, and we have a heat exchanger. This one, and we have a manifold, hydrogen manifold, and we have a filter, and we have a valve, and we have overpressure protection. Okay, and we have water inlet and water outlet. As I told, if you want to dissolve the hydrogen, you have to supply heat because it is endothermic reaction. So we are supplying the energy with respect to water. And also, if you see the metal hydrides, the problem is that this is very low thermal conductivity. Okay, so here, if you want to supply the heat to the metal hydrides to dissolve the hydrogen, obviously you have to enhance the heat transfer within the tank. So here we have used a spin type system heat exchanger to enhance the heat transfer in the storage tank. Now we can see the integration of metal hydride system with PEM fuel cell in electric golf cart application. So here you can see this is my fuel cell. Okay, backside of this golf cart, and this is my hydrogen cylinder that we have shown previous slide. So here you can see the various parts of this integrated system. So first one is metal hydride container. Okay, this one or this one. And second part is the buffer cylinder by using this compressed gas up to 100 bar. Okay, third is the pressure reducer. Okay, because this is having high pressure 100 bar. If you want to supply to the fuel cell, it has to reduce up to 4 bar. So that's why we are using the pressure reducer. Okay, and H2 recharge valve for recharging hydrogen whenever the hydrogen is dissolved from these tanks. So fifth one is heat exchanger from the metal hydride container. Okay, so this is our heat exchanger in the metal hydride container. And sixth one is air liquid heat exchangers. These are heat exchangers. And 11th is fuel cell stack. So here you see we have integrated these two are like thermal integration, because I explained the fuel cell reaction is exothermic reaction. If you supply hydrogen, it will generate both electricity as well as heat. So, and again, for this operation of the fuel cell, we have to supply hydrogen from the storage cylinder. Again, this reaction is endothermic reaction. We have to supply heat to dissolve the hydrogen. So we have thermally integrated these two, means one is heat supply, one is we need to supply heat to generate hydrogen. So we have connected these two with heat exchangers. Okay, it means these two are thermally integrated. One is generating heat, one is taking heat to generate hydrogen to supply to the fuel cell. So both are interconnected. So we tested this golf cart for different operating conditions. We'll see one by one. So what we have done is initially we have removed this buffer storage and we tested this fuel cell for golf cart. Okay, so it works almost 1 hour because we used a small container for hydrogen storage. Okay, just to test this integrated system, how it is working for golf cart. Then if you see this the temperature of this tank, so because of low thermal conductivity of this metal hydrides, okay, it is unable to supply heat fast, the required rate to generate hydrogen. So because of that, what it will do is it will dissolve the hydrogen, but it takes heat from itself, means the sensible heat it will take to release the hydrogen. So because of that, the temperature decreases, okay, inside the cylinder. Once the temperature decreases, the pressure also decreases as per our PCT curve I have shown previously. Because of that, this pressure output supply of hydrogen is less than the required pressure inside the fuel cell. Obviously, the fuel cell will stop. Okay, because of that, even though it is having some energy, hydrogen content in the cylinder, but it is unable to supply at required pressure because the temperature inside the cylinder is low. So it stopped after 55 minutes. Okay. Next, what we have done is we added some buffer cylinder. Okay. Then we have supplied the hydrogen from both the things. Okay. So you are taking less amount of hydrogen from the cylinder compared to previous case. Obviously, the temperature, the heat requirement will be less. Obviously, whatever you are supplying with water, that will be more than enough to stay the temperature constant. Before means going compared to in this case. Here you can see even the temperature decreases, but not much compared to in this case, because we are taking hydrogen from both buffer cylinder as well as metal halide container. Okay, so this operation continued operation almost 2 hours without having any problem. So here you can see this, we are taking the flow rate from both metal halide plus buffer cylinder. This is the hydrogen flow rate with respect to time, okay, for the fuel cell operation. And here you can see how pressure is decreasing, both metal halides and compressor. Okay, so this is combined flow rate from the metal halide plus this buffer cylinder. Here you can see the combined how much amount of how many liters we have given to this fuel cell with respect to time. It is increasing with respect to like both. It is supplying hydrogen to the fuel cell. Here you can see the initial part is mostly coming from this buffer cylinder, and after that we are getting more from metal halide, because once the heat started penetrating inside, okay, it will generate dissolved hydrogen. Okay, so initially we use this compressed gas buffer cylinder compared to this metal halides. Once the heat is transferred quickly inside, then the metal halide dissolves hydrogen. And also we have designed one more thing, that is hydrogen compressor for hydrogen refuel vehicles, because as I explained, if you want to have this hydrogen based fuel cell vehicles, you need infrastructure to refill the hydrogen. Okay, so for that we have like many ways to compress hydrogen. One way is you can compress hydrogen by mechanical compressor. Okay, but mechanical compressor, for compressing hydrogen, you have to supply high grade energy, that is electricity. Okay, that is not efficient way. Here we have developed the metal halide compressor. It can compress hydrogen by taking some waste heat from industries. Suppose you have a waste heat at low grade heat at 120 to 140 degrees from industry. So that heat as a driven force to compress the hydrogen by using this metal halides. So we have designed the 3-stage compressor, so that can compress, like we can take input is at 3 bar, I can deliver the hydrogen 200 bar up to like 5 Newton meter cube per hour. So I'll show here. So here we have 3 stages to compress the hydrogen from, like in first stage we use different composition, like we can supply the hydrogen from 3 bar to, we can compress up to 20 bar. Okay, then again second stage, by using different again material, we can compress 20 bar to 50 bar. Again third stage 50 bar to 200 bar by using again different materials, because these materials are choose based on their PCT concentrations. Okay, pressure versus temperature and concentration that I have shown earlier. Okay, so by using this low grade heat, you can compress the hydrogen without using mechanical compressor. So we have tested this compressor, so it is achieved up to 200 bar. Okay, so this system we can use for hydrogen refueling stations. Okay, so we have to generate hydrogen infrastructure for hydrogen based transport vehicles. So these are the material storage for different applications like automobiles. Okay. These are for space applications and industrial applications by using metal hydrogen to store the hydrogen. These are the fuel cell buses. Countries like Germany, we have Japan. Then I'm going to have like next topic towards energy storage. As you know that we are moving towards the renewable energy. Okay, so we have renewable energy, like if you take the solar and wind, we have huge potential compared to present world consumption. But the problem is these two are intermittent nature. Okay, the demand and supply may not match. So in that case, we should have some storage media to store the energy. Whenever your supply is more than demand, then that amount has to be stored, and whenever your demand is more than supply, then the stored energy has to supply to this grid. Okay. So the storage media is very, very important next 1 or 2 decades, because if you penetrate this renewable energy share, increase your renewable energy share in the grid, obviously the grid has to balance both supply and demand. Okay, so in that case, if you increase the renewable energy capacity like 20 to 50%, then obviously you need storage system, better storage system to store the amount of energy. If you compare the batteries, you cannot store a large amount of electricity, and also even though you can store the electricity in the batteries, but the capital cost will be huge amount. So here we developed some hydrogen-based renewable energy storage system. Okay, you can see the concept of the total hydrogen energy utilization system. Here we have a URFC. It means that unitized reversible fuel cell, means it can work as a electrolyzer as well as fuel cell. Whereas and one more thing, we have metal storage tank that I have explained before. So what this system will do, whenever you have a electricity supply is more than the demand, okay, that excess electricity will take and will generate hydrogen by using electrolyzer. Okay, then whenever your demand is higher than the supply from the grid, okay, so this stored hydrogen will be used to generate electricity by using fuel cell, so that electricity will be supplied to grid or applications. So in such a way that we can store this excess amount of energy from the grid, and also we can use deliver whenever your demand is more than supply from renewable energy source. So this system we can use as a storage media for renewable energy sources. And one more advantage is here you are not only producing electricity, we are also producing some heat. So that heat can be used for other applications like space heating, water heating, and all. And one more, if you go in for hydrogen-based vehicles, this stored hydrogen also can be supplied, used as a refilling station. Okay, this system can be used for refilling station. So to supply hydrogen to the hydrogen-based vehicles. So like this system, total system can store the intermittent renewable energy and supply electricity, hydrogen, and thermal energy. So you can see here this work I have done in Japan, the lab scale total hydrogen energy utilization system. Okay, you can see the URFC, and you can see the black one is the hydrogen storage tank. Okay, you can see the inner parts. So basically, it's having stack and DC load for fuel cell operation, and DC power for electrolyzer operation. We have chiller and water supply. Basically, this URFC having 10 cells, and each cell cross-section area is around 250 centimeters square. And in electrolyzer mode, it can take maximum 4.4 kilowatt. It means that you can supply in electrolyzer mode around 4.4 kilowatt, whereas in fuel cell mode, it can generate maximum 680 watt. Okay, so this is the construction of both URFC and metal hydrides. So this is the principle of unitized reversible fuel cell. Basically, it can work as a electrolyzer and fuel cell. Just you have to reverse this anode and cathode. That's all. The same components will use for both operations. Okay. So here you can see this is electrolyzer operation. So the hydrogen is generated at cathode. Okay. Anode side we are supplying water and electricity. Okay. So anode side we have again we are getting oxygen. Whereas if you see the fuel cell, we are supplying this hydrogen anode side, and we are supplying air, oxygen to cathode side, and we are getting some water and electricity from the fuel cell. So here we have used this membrane Nafion 115 as a membrane in the fuel cell, and the catalyst side we have platinum-based hydrogen side, and oxygen side platinum iridium oxide, and the gas diffusion layer like carbon paper that we have discussed, and oxygen side titanium felt. Okay, bipolar plate we have used titanium-based bipolar plate. Okay, this is our stack configuration in the URFC. Total we have 10 cells. So here you can see the flow field and various components of URFC. As I explained, this URFC combines both electrolyzer operation and fuel cell operation. Basically, it's a single unit. So it can reduce this number of components because the same components, the same piping we are using for both electrolyzer and fuel cell operation. Okay, so in that way, you can reduce the capital cost from both the devices. So you can combine in single stack. Okay, so here you can see we have 6 pipelines. These red pipelines are related to hydrogen pipelines, and this green one is related to air, and this blue line related to water pipelines. Okay, in electrolyzer operation, what you will do is you will supply electricity and you will supply water. Okay, basically it will generate hydrogen cathode side. Okay, and anode side you have oxygen with some water vapor. Okay, so this water vapor will supply to this separator tank. Okay, so we will take the water here and we will release this oxygen, and here also the water this hydrogen will be released with some water vapor, and that will be separated in the tank, and it is going to chiller. Even though if it is any water vapor is there, it will be condensed here because you are using low temperature fluid. So the pure hydrogen will go to in this way to the storage cylinder. So here using the back pressure to increase the pressure. Suppose if you want to have like 10 bar pressure from hydrogen generation, by using this backup pressure valve, you can generate the hydrogen at 10 bar. So in fuel cell operation, obviously this is different. Okay, you can see we are supplying hydrogen to here anode. Okay, so and cathode from air side. Okay, both will hydrogen from anode side and cathode side air is supplying. So basically this electrochemical reaction will occur. Okay, and it will generate electricity. And also here you can see we are using some chiller as well as circulation pump to maintain the temperature inside, because as I explained in fuel cell operation, that is external variation. So the heat will be released in the electrical reaction. You have to remove the heat. Okay, and we are controlling the temperature within the fuel cell. So in this way, we can combine that electrolyzer operation as well as fuel cell operation in one equipment. So that is the URFC. So as I explained, it can work as both electrolyzer operation as well as fuel cell operation, and also it can bring the capital cost down compared to if you use individual electrolyzer and individual fuel cell. And also it is having like higher operating ratio per one device. Obviously, this device will be used for like 24 hours almost, because either you will use one mode. If you have supply more, then you use electrolyzer mode. If your supply is less, demand is more, obviously you use in fuel cell mode. So you'll use more efficiently this UFC, and obviously less maintenance parts compared to individual systems. Hydrogen storage, as I explained, you can have like compressed form, liquid form, and solid form. Obviously, here this is stationary application. That you have to remember. This system is a stationary application. So here the weight is not a problem. Okay, so you can use the metal hydrides efficiently here to store the hydrogen at ambient pressure and temperature over a long period of time. So this is the schematic of metal hydride tank, which is developed at AST. So here you can see we have used that helical coil heat exchanger. As I explained, this absorption, desorption are like heat-driven mass transfer phenomena, and this metal hydride's thermal conductivities are below 1. Okay, so you want to increase this reaction kinetics, means absorption, desorption kinetics. Then obviously either you have to absorb, means remove the heat fast, or in absorption process, or you have to supply heat very fast in desorption process. Okay, so to enhance the heat transfer inside the tank, we use this double coil heat exchanger. Okay, so here we use this composition of Li is like magnesium bismetal based nickel Li, MMNFi, and the Li weight is around 50 kg. We use it here, and the total weight of this tank is around 85 kg. Okay, the size of the metal hydride is 500 microns. Okay, so and also here you can see we use some vacuum thermal insulator with thickness of insulation about 6 mm, and the aeroflex with thickness of 1 centimeter was wrapped around this metal hydride tank to reduce the heat exchange between this tank and surroundings, because we want to use this heat energy for further applications. So this system we tested for a sunny day as well as cloudy day. So as we know, the sunny day, you will get the solar PV. The power generation will increase up to afternoon, and again it will decrease. Okay, the same power we are supplied to the electrolyzer, and it is generated hydrogen. You can see the hydrogen flow rate with respect to time. Okay, the same pattern is same. Okay, so this works almost 10 hours based on your solar PV data. Okay, so after that you don't have any supply from the solar PV. Then what we have done is we have stored this produced hydrogen in storage cylinders. Then you just switch to fuel cell mode. Okay, so this is supply mode and this is generation mode. Then what we are doing here, we are using the stored hydrogen to again generate power by using fuel cell. So here this is your hydrogen supply from cylinder to the fuel cell, and here see you can see the corresponding power generation from the fuel cell. Okay, so initially we increase the step by step the power capacity to avoid the flooding problem, because at low temperature the flooding will be there. So here also you can see some peaks, because these are like every 5 minutes what we will use, we will recirculate the hydrogen, unused hydrogen, to the fuel cell. So that's why these peaks are there. So if you see that electrolyzer operation we have operated at 10 hours and fuel cell operation around 14 hours. So like this, the total day we have considered. And here you can see the result from metal hydride tank. So in as I explained, absorption is exothermic reaction. The temperature will increase even though we are using heat exchanger efficiently, means enhance the heat transfer, but still it will increase the temperature inside the metal hydride tank. This is absorption temperature curves. Whereas here you can see the fuel cell operation. As I explained, the hydrogen desorption is endothermic reaction. We have to supply heat, but still there the heat is not able to get inside efficiently, then the heat, it will take metal halide take heat itself, the sensible heat, the temperature decreases. But after that, once the heat supply is matching with your heat removal rate, then the temperature is almost constant. This is fuel cell operation, and this is electrolyzer operation. Okay. So these are the various performance parameters. I'm not going into it. Here you can see the schematic of energy flow, how energy flow is going to electrolyzer mode as well as fuel cell mode. So here we are supplying electricity to the stack as well as balance of plant. Okay, these are auxiliary supply. Then we are converting into hydrogen, the energy, and we have some waste heat lost, and we have some lost in the energy lost in electrolyzer. So this is first operation. And second operation, the stored hydrogen will be used to convert into electricity, and we have some heat lost that we have already taken. Then we have some balance of plant, auxiliary power supply, running the blower and running the pump. Okay. So this is how the energy will flows from electrolyzer mode to fuel cell mode. So these are the various performance data for sunny day. So we have achieved around 83% in electrolyzer mode, and if you combine the heat output, that will be around 95%, and this heat is from metal halides. Okay. So in fuel cell it is 24%. If you combine, that will come 51%. Include the heat output from this tank, it will come around 64%. Again, we tested same system for cloudy day, because as you know, this cloudy day, the power will be fluctuated. So we want to test how much it is withstanding with respect to your fluctuation power. Stable power, obviously, it will generate efficiently, but we want to test here how this electrolyzer working with respect to this fluctuation power. Okay, without having any deterioration or operation problem. So here you can see the power supply as well as the relevant hydrogen flow rate from the this hydrogen generated from the electrolyzer. You can see this electrolyzer works efficiently even though your power is fluctuating in this cloudy day. Okay, then again similarly we have operated again 14 hours operation fuel cell to generate again get back that electricity by using the stored hydrogen. So you can see the results for metal halide tank. This is the fluctuation because of our hydrogen fluctuations. Okay, once if your hydrogen is low, then your reaction rate is the heat generation is low, then obviously the temperature will decrease. Again, it will increase. These are the performance data. So here, what you have achieved is, even though the power fluctuation is there in partly cloudy day compared to sunny day, but the efficiency is not deteriorated. Okay, that is the advantage of this URFC fuel cell. So the same system recently this developed at Germany. Okay, you can see this Berlin airport project. The same kind of system is there. Here, what they are using is they're using this wind farms. Okay, that will be connected to grid. Okay, and the excess power, whenever the wind power is more, okay, that will give to electrolyzer for hydrogen generation. Okay, that will be stored into hydrogen storage tank. Okay, the heat will be generated to here. Okay, this here they are storing hydrogen, and the stored hydrogen will be supplied to the CHP plant. That means the fuel cell for heating as well as electricity. Okay, so the stored hydrogen also will be used for the hydrogen refilling station. Okay, this is for refilling station to refill the hydrogen based vehicles. This is one of the pilot plant for this kind of like hydrogen based energy storage application. Okay, so here they used around 40 wind energy conversion devices. Okay, these are 40. Those are like each one is 1.8 to 2.3 megawatt each, and the electrolyzer used here is 500 kilowatt, and 2 CH2 units with 100 kg metal halide storage. Mean each one is 100 kg metal halide. Okay, the H2 filling station is around 450 bar. Okay, it can refill the hydrogen at 450 bar. So that is the advantage of this pilot plant in Germany. Okay, same thing we can use for this solar thermal power plants. I think you know the advantage of solar thermal plants compared to solar PV. So the solar PV obviously this cheap technology. So you can generate the power like 2 to 2.5 rupees per kilowatt hour compared to solar thermal. Solar thermal now the least tender cost is around 7 rupees in Middle East. But the advantage of solar thermal compared to solar PV is here in solar thermal you can store the energy compared to electrical energy. Even the electrical energy also you can store, but the cost of storage is less in case of thermal storage compared to electrical storage. So this I think you know that. And we have different kinds of thermal storage systems. One is sensible, latent, and the reversible chemical. So sensible and latent, if you compare with the latent chemical storage, the density, energy density is low for sensible and latent. We can use some metal halides for storing the hydrogen. So here I have shown the system here. We have two systems. Okay, one is high temperature and low temperature. So whenever you have this thermal energy is more than this your heat exchanger requirement or cycle requirement, means the power conversion cycle. Like so, suppose you have 50 megawatt power conversion plant. Okay, basically if you have turbine 50 megawatt, and obviously you have to supply the thermal energy almost 3 times more than 50 megawatt because the conversion efficiency around 30 to 40%, right? So you will supply this around 150 megawatt of thermal energy, or maybe around 120 to 130 megawatt. But sometimes what we do is we'll have the solar panels with more capacity than this 130 megawatt. So that heat, the extra heat will be stored here during morning time. What will happen? You supply this heat to this metal halide, it will dissolve and it will go to low temperature metal halide. It will release to water at 30 degrees centigrade. Once your morning session is over, then during night evening session, you supply this water again. It will generate hydrogen and it will supply here and it will release the heat. Okay, so that heat we can use for during evening hours or night hours. So in this way, we can use this technology as a energy storage option. That is the metal hydride based thermal energy storage system. So these details will be more you can get from Professor Anil Kumar from IIT Tirupati. So this is the operating principle. As I told here, we have two reactors. One reactor will dissolve the hydrogen and the second reactor will absorb the hydrogen at different operating conditions. So here I will show this. We are passing the heat transfer fluid and it will dissolve hydrogen and the same thing will absorb by another reactor and that heat we are taking. Okay. By playing this the temperature and pressure, we can store the hydrogen whenever can store the hydrogen as well as heat whenever just excess supply, and again we can take back that heat. So this we have done at this one at IIT Guwahati to store the heat storage by using metal halides. Okay. This is the CO2, the heat pump based on the solar thermal concentration. By using metal halides, you can also generate the low temperature applications. And here you can see this the future energy system where we are using both electricity as well as hydrogen as a energy carrier, and we are generating this electricity as well as hydrogen by using CO2 free primary energy like renewable energy. We are generating electricity as well as hydrogen for users like transport applications and other industrial applications. In this way, we can reduce the global warming as well as and the dependency on the oils from other countries. So here I can show one more example of this photovoltaic solar hydrogen system in Norway. So they are using the same kind of technology to store the hydrogen of store the energy from wind energy. Okay, so they have some island. Okay, there they're producing, because this island is not able to connect to the grid. What they are doing is they are generating power by using wind farms. Okay, and also as I know that wind farms like wind energy, you cannot get continuously same amount. Okay, these are basically intermittent nature. So this some amount of energy will be stored in place of hydrogen by using electrolyzer, and the same thing you can convert back to electricity whenever you have wind power is less to the grid. So this is the one more example in Norway Island, the same technology. So here you can see the various hydrogen cars developed by various companies, like we have Hyundai Nexo and we have Tuscan FCB by again Hyundai company, and we have the new hydrogen fuel buses developed by the Hyundai. Okay. Then you can see what are the challenges for hydrogen economy. So first, obviously the production side, the price of the hydrogen generation has to get has to go low, because now the cost is around $10 per kg of hydrogen. It has to go below, then only it can sustain. Then coming to storage, storage, like still we have to develop efficient storage media to satisfy all the conditions set by the DOE. Again, distribution, we have some problems like delivery, the pipeline infrastructure has to create entire country. That is the major drawback. Then the utilization, other than fuel cells, we have to have like other applications for cooking, okay, and various applications. We have to do research for hydrogen-based systems. So thank you. So if you have any doubts, I can clear.
Dear participants, please unmute yourself and you can interact with Satyashekhar sir. If you have
I have
any
not taken
doubts.
extra time. I'm in time. Anyway, no problem, because I have shown the applications of the technologies, but the basic technology will be shared by the Professor Nagasrinivasulu, basically from the fuel cell fundamentals, design of fuel cells. And if you see the metal hydrides fundamentals will be taken by Professor Anil Kumar. So I have shown that some applications of this both the technologies.
Any clarifications required for the participants? Please interact. Sir, we are not receiving any.
It's okay, sir. If you have if they have any queries, they can contact directly through email or through phone number.
Okay, sir. Thank you very much for sparing your valuable time for us to deliver the lecture, and you have given a wonderful session for our participants. So this might be very useful for participants. to do the research work in this fuel cell technology. So once again, thank you very much, sir.
Thank you, sir. Thank you once again, for giving me the opportunity to talk about hydrogen economy in this FDP.
So I will send an email to you, sir. Please go through that.
Yes, sure, sir, sure.
Sure.
Yeah.
Sir, we'll close it, sir.
Yeah. Thank you, sir.
Thank you, sir. So this is the morning session of today's FDP. In the afternoon session, so we have the topic on biomass energy by Narsimula Sankhe, Professor of Mechanical Engineering at Osmania University, Hyderabad. So all of you join at 2 o'clock sharp. Thank you.